So the graphs of trig functions means the 6 trig functions. The first two have their own section. That's section 4, 5, and that's sine and cosine. The next 4 are in the 4, 6. Sine and cosine are very, very useful. I mean, you use those all the time. I'm not so sure what the applications are for the others here, as far as the graphs go. I mean, the functions come up, but do we really use the graphs so much? I've never seen it that much. So mostly, if there's real world stuff to this, it comes from the first couple. It comes from sines and cosines. Now, the sine, in order to get this graph for a sine function, you're going to use your unit circle, right? You're going to understand that, remember the sine? I mean, you just have to picture this, but the sine is the y-coordinate on the unit circle. And we know that the y-coordinate at 0, at the angle of 0, is 0. And then the y-coordinate at pi over 2 is 1, right? And then at pi, it's back to 0 again. And at 3 pi over 2, it's negative 1. And then if we go all the way around the circle once, then that's 2 pi. But it's actually the same place that we were when we started. So it's back to 0 again. So this is what you call one period of the function. When it starts here, right? Undo, edit, undo. Blue. Right, it starts here. And it ends here, because at that point it's gone through one complete wave, right? And how long did it take to do that on the x-axis? From 0 to 2 pi. That's why they're saying here, the period of the sine function, just the regular old y equals sine x is 2 pi. Now, if I keep going around the circle, then that means I keep drawing this wave to the right. And it's just going to keep repeating itself over and over and over again. Notice that, we know where did the values for the actual sine function come from? Since they're the y-coordinate, and this is the y-coordinate for all the points on a circle, which has a radius of 1. So you're never going to get a value more than 1 or less than negative 1. That's why it goes down as far as negative 1, goes up as far as 1, and it just repeats itself. So you would say the domain, this thing goes on forever to the left and forever to the right, so the domain is all real numbers, and the range is -1 to 1. Right? And the period is 2 pi. Now, if you look at the cosine, it's the same shape, right? It just starts different. Because now, since we're using the x-coordinate, and the x-coordinate at the angle of 0 on your unit circle, the x-coordinate starts at 1, right? And then at pi over 2, it's down to 0. Right? At pi, it's down to -1. Remember, at pi, it's -1, 0, so there you go. And then at 3 pi over 2, and now you're back again to 2 pi, and it's back to the same place that it started. So it's the same shape, it's just it has its peak, and its max and its min in different places. It's got its zeros in slightly different places, but it's basically the same shape. So sines and cosines are useful if you're going to model things that are like waves, right? Like the waves in the ocean. Anybody think they want to go into some kind of oceanography or anything like that? Well, you're going to be using models that use this kind of thing. In the atmosphere, obviously, I mean, if you just think of the patterns of things like temperature, like the temperature is such a nice subject today, right? So cold out there. But it generally has a maximum, and then it has a minimum, and then it has another maximum, and it has a minimum. I mean, that's kind of what's going on with the temperature, and we know it goes on forever. So you kind of need a function like that to model it, and we do. In fact, it relates a little bit to the linear speeds and angular velocities and things like that. If you imagine the Earth, right, here's the equator in the middle there. And we know how fast the Earth is going around. right? That's an angular speed. It's going around, you know, one revolution in 24 hours. So you could work it out in whatever units you want, but that's how fast it's going around. Now, if you take a particular, what we would call a parcel of air in the atmosphere, okay, as it goes around with the atmosphere, then it's actually tracing out an arc length, right? I mean, it has a path in the air, which is going around like that. So if it's farther up, then it goes around a bigger circle. If it's closer in, it goes around a smaller circle. But if you just imagine one parcel of air, which is right at the equator, and let's say it's spinning around with the Earth exactly with the speed of the Earth. And so it's tracing out a circle which is big as, let's say, the radius of the Earth plus some fixed amount. If that parcel of air starts to go towards the north, then the circle gets smaller, right? As you go up, then the distance around the Earth is smaller, but it's got the same speed. It doesn't lose. There's a conservation of angular momentum here, which is going to make that thing go the same speed even as it goes up. Well, if it goes the same speed as it goes to the north, then in the same day that it went one time around when it was at the equator, it's going to go more than one time around when it's higher latitudes, right? It's going to go one time around, but that's a smaller circle, and then it's got to go a little bit more. So it's going to go around once and a little bit to the right. And as the radius of the circle gets smaller, it keeps going more to the right and more to the right. The opposite would be true if you took a parcel of air which is at the North Pole, you know, or with a very small circle it's going around. As it starts going to the south, as the circle gets bigger, it's actually not getting all the way around the circle anymore, right? Maybe at this spot it's getting one time around in one day, but then when the circle got a little bigger, it's not getting quite around. Maybe it's only getting to here. So what the effect of that is that things that are coming up from the equator are being deflected to the right. Things that are coming down from the pole are being deflected to the left. Now that is kind of the forces that are out there in the atmosphere, because the pole is really cold and the equator is relatively hot. You know, I mean, just imagine that you had a pan of water and you had like a divider in the two where you could like heat one half of the pan to be really, really hot, and then the other to be really, really cold. And then you took the divider out. What would happen to the hot air, the hot water on this side and the cold water on this side? It would try to mix, right? I mean, that's just nature would try to mix the differences and make them the same. That's what's trying to happen here. The warm air is trying to go to the north. The cold air is trying to go to the south, but they're not getting there because of the radius of the Earth and spinning Earth. It's actually this air is being deflected to the right. This air is being deflected to the left, and it's building up what we would call a gradient of temperature right in the mid-latitudes, right where we're at, okay? So the atmosphere, because this is an unstable state of affairs, breaks into waves, because waves is a more efficient way to bring the cold air south and the warm air to the north, right? So that, you know, if you look at the weather map is usually made up of waves and things like that, specifically in the mid-latitudes, and it's because of that. So these kinds of graphs, sines and cosines, are pretty useful. I mean, they're really useful in meteorology. That's it. Now, what we're going to be doing today, we're going to be doing with the calculator, and your homework is going to be doing the same thing. So you need to know how to set your calculator so it is doing the same thing that I'm doing up here. So remember on the calculator, do I have my calculator up? I've copied the screen a little bit here, right? The window is right there. So wherever it says window, when you click on that, you want to set your window to be the x-min -2 pi, right? Use the pi key there. And the x-max +2 pi. And then the tick marks in between, set it to pi/2. And then the y-min, let's say -2. The y-max, we'll say +2. And we can make the scale 0.5. And you definitely want to be in the mode, you want to be in radian measure when you're doing a graph. If you set it to degrees, you don't see anything on the graphs. So set it to radians. So once you've got all this stuff set, then we're ready to fly through these slides to understand this stuff. Is everybody set? Set? Courtney? Okay. Taylor? Okay. Okay. So first, the graphs of sine and cosine. They are a pi over 2 shift of each other. I mean, you can see that the maximum on the sine graph is at pi over 2. The maximum on the cosine graph is at 0. So that is, you know, exactly a pi difference of each other. Other than that, same graph. Now, the general equation of a sine function is this one right here. Now, the variables are x and y. The a, b, c, and d, those are constants, which we've done this kind of thing before where we transform or translate graphs based on what we add, subtract, add and subtract and things like that inside the function, after the function, putting minus signs in front. I mean, all those things that we've done with every other kind of function, we got to explore how does it work with a sine function. And by implication, it's the same with the cosine. We don't really need to do them both. Now, you can see that this constant right here sometimes is written at the end when you see it. It doesn't matter. It's still just a constant, right? It's not part of the sine function term at all. So now the first thing we're going to look at is the a, right? What's the effect of this a, which is multiplying times the function? And I do that by, and you could do the same thing in your calculator if you want. You could, on one line, you could put sine x. On the other line, you're going to do 2 sine x. And you would see these graphs. Right? What does it look like happen to the graph when we've multiplied it by 2? Yeah, I mean, in a way, remember when we multiplied other functions by a constant, that was either called a stretch or a shrink. So this is a stretch, right? That a is stretching the graph. Now, sine and cosine in particular, because of the wave nature that they've got, then, you know, they have the middle of the graph is here. They are going up a certain distance and down a certain distance like that. That distance right there is called amplitude. Amplitude. Right? It's how much above and below the middle is the graph going. It's like the wave height, I guess, if you were doing that in the ocean. So we see the effect of multiplying by a constant. It stretches the graph, and we introduce the concept of amplitude. So right now we have the concept of the period of the graph is how long does it take to go through one wave. The amplitude of the graph is how high does it go above and below the middle. Right. Now, so this A right there, and we say absolute value because even if it was a -2, we would still say the amplitude is 2. Right. I mean, whether it's going above or below, it's like an absolute value. It's the positive distance from the middle. So that explains the A part of this. I think I have another one which adds to this a little bit. You know, I mean, notice the difference now between the sine 2 or 2 sine x and -2 sine x. What's the difference in the graphs? I mean, what does it usually do when you put a minus in front? It flips it, right? So this piece of the graph is now here, right? And this piece is now here. So basically, you know, if you're starting at 0, 0, if there's a minus in front, it's going down first instead of going up first. But the amplitude is still the same, right? How high it goes above and below the middle is still the absolute value of -2, which is 2. right? So amplitude's always positive. Okay, now let's look at the B. The B is the bx minus c part by comparing sine x to sine 2x. Okay, what's the difference in these graphs? You know, this one had a period of 2 pi, right? It went through one complete wave between 0 and 2 pi. What about this one? It's actually going through 2 waves between 0 and 2 pi. So actually the period of this thing is pi, right? It's going through one complete, 0 to maximum to 0 to minimum to 0, back again to the start, in just pi. So the effect of multiplying the x inside the function is to change the period. Right? That B affects the period. Now, actually, there's just a teeny bit of a formula that you got to use to calculate the period. Right? The period is 2 pi divided by whatever that constant is. So when you just have sine x, the B is 1. So the period is 2 pi. When you have sine 2x, the B is 2. 2 pi over 2 is pi. So as the numbers get bigger, the graph goes up and down faster. Notice this one. Now I'm going to do sine x compared with sine x over 2. So what is the value of B in sine x over 2? 1/2. Right? What is multiplying times x? 1/2. So I use our formula. 2 pi over B is 2 pi over 1/2, which is 2 pi times 2, which is 4 pi. So by having a number which was less than 1 for B, it made it go up and down slower. I mean, notice this one went through one period from 0 to 2 pi. This one's going through one period from negative 2 pi to positive 2 pi. It just gets through 1. Okay, so that's the B. Right, now we got to look at the effect of the D. Well, what does it usually do to the graph of a function when you add a number after the function or before the function? It's a vertical shift. Right? So when I add 1, if I do a 1 plus sine x, it takes this graph and moves it up 1. It's exactly what you would expect, and that's what it did. It just took this graph and moved it up 1. That's the effect of the D. It's just a vertical shift. No different than we've done before, right? Plus means up, minus means down. Even if it was at the end. I think sometimes the reason why they show it there is because, let's say you had a function that looked like this. Y equals the sine of x plus 4. I think by putting it at the beginning, it makes it clear that that plus 4 is not part of the sine function. It's not intended to be like the sine of parentheses x plus 4, which it won't be. But you might confuse it that way if you wrote the plus 4 at the end. If you wrote the plus 4 at the beginning, no chance for confusion. Right? I think that's why they do that. So far we've said A affects the amplitude. We defined amplitude. B is period. That gives us the formula, 2 pi over B. D is the vertical shift. And then what do you think is going to happen by adding or subtracting inside the function? Horizontal shift, right? Which it always was the effect of adding and subtracting inside the function, was that. So now let's compare these two graphs. Sine x and sine of x plus pi over 2. What's the shift usually when you add inside the function? Is plus mean left or right? It usually means left, right? And that's what is going on here. If you take this graph, the sine, and notice that it had a maximum at pi over 2, but when we added the pi over 2, now it's got a maximum at 1, which is less, it's pi over 2 to the left. Now, yeah. And then this is the cosine, right? That is the cosine. So we can say that the sine of x plus pi over 2 equals the cosine of x. And if you look in your book, I don't know if it's in the back cover or the front cover, where they have all those identities, that's one of them. So it kind of makes sense. Now, it's not that clean, all right? We're not ready to say that the C is the horizontal shift. It's a little more complicated than that. Look at this one. Now I'm comparing the sine of 2x, which we know has a period of pi, and the sine of 2x plus pi over 2. Now, if what we just said in the last slide was that pi over 2 is a shift of pi over 2 to the left, you would see that that's not correct. It did not shift it pi over 2 to the left. It actually, this thing, because it had 2 periods, the period was only pi, it had its maximum at pi over 4, not at pi over 2. And this thing has its maximum at 0. So it's actually only a pi over 4 shift to the left. So it's actually, we do learn about the horizontal shift from this, but we have a little bit of a formula for it. The formula is C over B. You got to divide this number by this number. That tells you the horizontal shift, right? So here, if I do pi over 2 divided by 2, there's your pi over 4, right? That's how you get the horizontal shift. And it's still, if it's a minus, that means to the right. If it's a plus, that means to the left. So that explains all 4 of those constants and how they affect the graph. Okay, that puts it all on one side, which you may have already been doing that, but that just puts it all on one. So I'm going to do this just to show you the homework problems and how we're going to end up doing those. You're going to use your calculator. Okay, we're going to set our window so that we want to go on our window settings. Right, from minus a period to plus a period. And zero will be in the middle, and then after you've calculated the period, make the x min the one period to the left, or a minus, right? And then make the x max a period to the right. And then you could set your scale whatever. It doesn't. That just changes the tick marks. It doesn't matter. That's for the x. For the y, we're going to make the y go from the min to the max. So you have to understand just a little bit about the function to figure out, how do I know what the min is and the max? But once you have it set, what that means is when you graph it, you're going to have a graph that goes from the bottom of the screen to the top of the screen. Exactly, right? Otherwise, you did something wrong. So on this particular problem here, first, let's figure out the period. So what is the formula for the period? Right, period is 2 pi over b. Well, what is the b? X is, or the b is 1, right? Because you don't see a number there, it's a 1. So this one, it's 2 pi over 1, which is 2 pi. So we're going to set, it's going to go from negative 2 pi to plus 2 pi. I think we already have it set like that. Okay, now, what are the two things in here that affect the minimum and the maximum? Does shifting horizontally affect the minimum and the maximum? No. Does the period affect the minimum and the maximum? No. The two things that affect it are the amplitude, which is telling you how much it's going above and below the middle, and then the vertical shift. Like in this one, if there was no vertical shift, the amplitude is 4, so what would be the minimum and the maximum? It'd go negative 4 to 4, but everything is shifted up 4. So it's actually going to be from the min should be negative 4 plus 4, which is 0. And the max should be positive 4 plus 4, which is 8. So we want to set our window from 0 to 8. So go to your calculator. Oops. Can I do that over here? Darn it, I guess I got to get rid of this stuff. There. And window set. So the x is going to go negative 2 pi, negative 2 second pi, enter. Positive 2 second pi, enter. Again, I'm going to make it pi over 2. Second pi divided by 2, enter. I'm going to make my y go from 0, it already is, to 8. And the scale of 1 is good. And now I'm going to enter the function. Oh, make sure I got my mode right. I'm in radians, so now let's go back and put that in. 4 times 4 cosine x plus second pi divided by 4 in parentheses plus 4. Okay, graph. Okay, so you could see that it's going from one period, right? It started here, it went down to its minimum, it went up to its maximum, it came back to the same spot. There's one period. To the right, it goes through one period. The graph is going from its minimum to its maximum. So you want to sketch the graph, just copy the graph. And show it, right? This one went something like this. Come on. Just sketch it as best you can and then label those things that we calculated to get that, right? This goes from negative 2 pi to 2 pi, right? It's going from 0 to 8. Everybody should have exactly the same graph when you do this. Just copy the screen the best you can, label those things that you use to set the window, and that's it. I think this is probably where we seem to have the most trouble, is with the min and the max, setting the min and the max. But just try to imagine the basic cosine function goes from negative 1 to 1. That number is changing that, right? So that goes negative 4 to 4. That number moves it all up. Those are the only two things you have to take into account to set the min and the max. Okay, one more. Okay, so the period is two pi over b. Okay, what is the b? 2/3, right? The b is 2/3, so again, which is 2 pi times 3/2, which is 3 pi. So we're going to go negative 3 pi to positive 3 pi. Okay, what is the minimum and the maximum of this graph? What is the amplitude? The amplitude is 4, right? So it's going to go between negative 4 and 4. I mean, the fact that it's got a minus doesn't change the amplitude. It does mean it'll go down first instead of up first. But it looks like, and there's no vertical shift. So the min and the max are min, negative 4, max, positive 4. So let's set our window. Window. Clear. Clear. So 3 second pi. Enter. 3. Oh, that was wrong. Negative 3 second pi to positive 3 second pi. From negative, scale pi over 2, that's good. Y min is negative 4. Y max is 4. And I'll leave the scale alone, and now I'm just going to enter the right function here. Negative 4 sine 2x over 3 minus pi over 3. Graph. Right? So it looks like it's going from the bottom of the screen to the top, right? So we got the min and the max set correctly. It looks like it's going through one wave, right? It's this kind of scarily, it's just like the other one, right? It had its maximum just to the left of the 0, but it is definitely one wave. It started and ended at the same spot, to the left and to the right. So just copy the screen, label the min, the max in both directions, the period. So there's 2 homeworks like that. It's purely a calculator exercise. Once you've calculated the period, the min, and the max. I don't know what's next. Now, the tangent, their next 4 functions, right, are all characterized by asymptotes, right? And where do asymptotes come from in any function? I mean, how do we figure the vertical asymptotes in a polynomial? It's zeros of the denominator, right? Well, all of these things have denominators that could be 0. Tangent, which we saw in the identities, tan x equals sine x divided by cosine x. Okay, well, where is the cosine 0? Just think of the unit. This is where your knowledge of the unit circle comes into play. Cosine is 0, the x-coordinate, at pi over 2 and 3 pi over 2. So looking at this graph here, there's an asymptote at pi over 2 and 3 pi over 2. And then if you go in the negative direction, that's negative pi over 2 and negative 3 pi over 2. Right, so the asymptotes, right, it's where the cosine equals 0. And then the zeros of the function are where the sine equals 0. And you can see they got these big black dots to represent the zeros, right? So wherever the sign we know is 0, it's 0 at 0, and then it's 0 again at pi. So there's a 0 at 0. There's another at pi. There's one at negative pi, which we know is coterminal with pi. But it's just repeating itself. It's got one branch in between all those asymptotes, which means it does not have a period of 2 pi. I mean, how much, what's the interval on the x-axis through which it goes through one cycle, one period? It's actually from negative pi over 2 to pi over 2. That's just pi. So the period of the tangent is pi. It's not 2 pi like sine and cosine. It's pi. Okay, so zeros where sine x equals 0. And then there's no concept here of amplitude because this thing doesn't just go up a certain amount and come down. I mean, it approaches a vertical asymptote by going off towards infinity or negative infinity. So amplitude is out. We're not dealing with amplitude anymore. That's a sine and cosine thing only. And then notice this way of saying what the domain is. The domain is x does not equal, right? And it's got pi over 2. That's certainly true. And then it says plus n pi. So what it means is multiples of pi. I mean, just go on your unit circle, right? Which I don't have up, but the cosine is 0 at pi over 2. And then if I add pi, I'm down to here, right? So if I add pi again, I'm up to here. If I add pi again, I'm back to another place where cosine is 0. So in the end, it's n pi over 2, where n is any integer, right? Positive or negative. And there's infinitely many of these because it goes on forever. The range is all real numbers, right? That goes on forever, up and down. Right? The cotangent is 1 over the tangent. So cotangent, if we want to do this in terms of sines and cosines, is the cosine of x over the sine of x. Again, it's going to be characterized by asymptotes because whenever that denominator equals 0, you got a vertical asymptote. Now it's not where does cosine equal 0, it's where does sine equal 0. So the zeros of the last one become the asymptotes of this one. Sine equals 0, that's 0, pi, 2 pi, negative pi. Right? It's multiples of, I mean, you could say it like x equals 0 plus n pi. There's no point of writing the 0. So just multiples of n pi, that's where you find your asymptotes. And the zeros, again, where it crosses the x-axis, now they are at wherever the cosine of x equals 0. Pi over 2, negative pi over 2, 3 pi over 2. And I just find it interesting that on these two graphs, on the other one they made these big black circles to designate the zeros, and on this one they didn't. And if you notice, and kind of expected, I mean, its period is pi. Just like with the tangent, the period is pi, not 2 pi. Okay, so if we had to graph something like this, we're going to set our window to minus a period to plus a period. Same thing, right? Minus a period to plus a period. And in the y, because these things go on forever, I'm just going to make it a fixed -5 to 5. So it'll always be the same thing. There's nothing to calculate. There is no min, there's no max. So in this case here, and then the other thing is, so the formula for the period now is not 2 pi over b, it's pi over b, right? So period equals pi over b. What is the b? The b is here, right? So it is pi over 2. So you're going to set this thing from negative pi over 2 to positive pi over calculate. So window, negative second pi divided by 2 to positive pi divided by 2. And I'm going to leave that one alone. I'll go negative 5 to positive 5. And I'll put the function in, clear. Where I'm at, negative tan 2x. That was wrong, clear. Negative tan 2x. Graph. So when you sketch it, you should include the asymptotes. I mean, you can see where they're at, right? They're right here and right here. And then label asymptotes in the window, right? Negative pi over 2 to pi over 2. Negative 5 to positive 5 in the asymptotes. Try this again. So this is going from negative 5 to positive 5, from negative pi over 2 to pi over 2. What is the equation of that line? It's halfway in between 0 and pi over 2. Where is it? Pi over 4. So you need to say x equals pi over 4. X equals negative pi over 4. And just copy the graph. Now, the secant and the cosecant have kind of different graphs. Right? The cosecant, remember, is 1 divided by the sine. So clearly, it's going to have asymptotes wherever the sine equals 0. There you go. But it does not have zeros because the numerator of that fraction is a 1. There's no way that fraction ever equals 0. So you don't see it crossing. Now, the period, if you notice, because it's based on the sine, and the sine had a period of 2 pi, so does the cosecant. Right? It's got one branch here, and it's got another branch here. That's all between 0 and 2 pi, and then it repeats itself. Right? And then it repeats itself. Remember, all of the sine is a wave that goes like this. So, of course, wherever the sine is 0, there's got to be an asymptote. If the sine is 1, then 1 over the sine is 1. But if the sine is like this, it's like less than 1 and positive, then when you divide, 1 divided by that, then it's bigger than 1. Right? 1 divided by a number less than 1 is a number bigger than 1. That's why these things go up from that point. And the same thing with the secant. Now, the secant is 1 over the cosine. So it has to have asymptotes wherever the cosine equals 0. And it does not have any zeros because the numerator of that thing is 1. And if I sketched in the cosine function, it would make sense out of all of this. So that again, there's the cosecant and the secant. You get overlapped with the, I mean, this is the cosecant, so there's the sine, and this is the secant, so there's the cosine. You can see the relationship between the two. Expected, right? So if you're going to graph one like this, again, we're going to use the same settings, minus a period to plus a period, and -5 to 5. In this particular problem, we're back to calculating the period as 2 pi over b. In this case, 2 pi over b, the b is pi over 2. So 2 pi divided by pi over 2 is 4. Right, the pi's canceled. 2 divided by half is 4. And that gives us what we need to do there. Now, the rest of it, oops. So let me go set the window. So we're going to go from -4 to 4. And I'll make that a 0.5. And then I'm going to go from -5 to 5, just like we've already got it. Now, how are you going to enter the secant function? 1 divided by the cosine, right? Or you can use the cosine again, hit the x to the -1, whichever way you want to do it, but that's how you're going to have to enter it, because you don't have a secant function on here. So let's see, 1 divided by 3, 1 divided by 3, and then it'll be times 1 divided by cosine pi x over 2, second pi x divided by 2 plus second pi divided by 2. Graph. So it looks like we got 1 period to the left, 1 period to the right. It looks like there's, notice that we don't have an amplitude, right? There's no such thing as the amplitude. But in this case, because of the 1/3, that means that the graph is going down as far as positive 1/3, and it goes up as far as negative 1/3, right? It's a little bit closer because of that, but it's not really an amplitude. So the main thing, if you got everything that we did up to there, is just remember, if you're going to do secant, cosecant, and cotangent, you're going to have to do the 1/over thing to actually put the function in there. So I wasn't able to talk about the word problem thing because we only had an hour today. These are definitely exactly like we just did in class. And if you look at the last example in the first section, 4-5, you'll see that. Are we doing that?